Hi everybody, welcome to lecture 15. We're talking about a new topic called floating point. Caches are not necessarily a prerequisite for this, so this could have occurred earlier. We happen to put it now because we want to make sure you saw caches by the time of your project. So a quickie thing here is a space bar. Hello to Ahmed Bajat from Penn State. Give him some love for listening in. Again, anybody watching online, listening online, email to me, ddgarcia@csberkeley.edu, and we'll give you a shout out. Also, there's an HCAM review session this weekend, which is on Saturday afternoon, and our review session is going to be next week. We'll announce it. We have a Thursday exam. We're looking for temporarily if we can find a space to hold 300 people on Tuesday. But we won't explicitly tell you where and when until we get the room, but that's the hope. That'll give you 2 days to prepare. So there's two steps. This is really walk in, I'm clueless, what's my answer? And then the 61C is really hoping you've seen something and are ready to ask some real good questions. So this is a great discussion of the news of the day, Kumi's law. So Stanford professor Jonathan Kumi, looked at 6 decades of data. This is real stuff. This is like as important as looking at, whenever you have 100,000 or 1 million samples for, say breast cancer or something like this. This is a lot of data, folks, 6 decades of data, and found that even pre-transistor, a law, he didn't say it's a law, he said, I'm so honored to be called a law. He came up with this idea just like Moore did. Moore didn't say it's a law. Moore said, I have this idea of this prediction, I have this idea of this pattern I'm seeing. He said, in 6 decades, it turns out that efficiency doubles every 18 months. That's relevant if you're a battery-powered devices because it means that if you have to do the same amount of compute power, that if you just wait 18 months, on average, you can do it for half of the energy. That's pretty cool. So good stuff. Important for those of us who are at mobile devices. James Gosling's son guy, we're talking about floating point. I was playing the song Float On by the Floaters in the 70s. 95% of the folks out there are completely clueless about floating point, and that's because they haven't come through 61C. So, you remember in the early days, we saw n bits, and we can encode those n bits a lot of different ways. We can treat them as n 1-bit values. We could say, we'll cluster them by 8s and consider them as characters. We can cluster them as one whole thing, considering 32-bit quantities, say, as MIPS instruction. We can also think of it as integers, you saw that, and we can count from 0 to about 4 billion if it's unsigned, or minus 2 billion to positive 2 billion if it's signed. That's all review. But we have yet to talk about what happens if the number is bigger than 4 billion, or really small, or even in the middle, but just has a fractional part. We really haven't talked about that enough. So today, we're thinking about that. We'll just try solving the 1.5 case first and see what we can do there. So we kind of talked about this in the peer instruction question of putting this binary point in there and considering this just flows smoothly from this leftmost x is the 2's column, 2 to the 1 is 2. Then the one right to the left of the dot is the 1's column, 2 to the 0 is 1. You keep going seamlessly, it goes 2 to the minus 1, or the halves column, the halves bit, and the quarters bit, 2 to the minus 2, the eighths bit, the 16ths bit, okay? And so this is called a fixed point. If you always freeze it there, and I always consider these 6 bits, I'm going to give you 6 bits, but you and I have an agreement that there's a fixed point after the first 2 bits. Then I'm going to be able to represent numbers from 0, unsigned here, of all zeros, right? 0 and a 0 there, to 39375. How close is that to 4? Anybody? A 16th. Why is that, Rohan?
Because the least significant digit is a 16th.
Because I count by 16ths. That's exactly right. I add one more 16th bit, the whole thing would roll over to 4. It would be a 1, which I can't represent in this notation, 0, 0, 0, 0, 0, and I get to exactly 4. Exactly right. It's a 16th away from 4. Well done. How did he also know it was a 16th away? Because he did a quick subtraction of this from 16th and get 0.0625, and he's memorized this table, which is that a 16th is 0.0625. And I once asked 61C students, spring 10, wouldn't it be cool to visualize this by color coding 0 as black, 9 as like white, and then have a black body heating diagram? What would this look like? Are there any patterns? And the top student I found was Mark Liu, who generated this thing within a day, within hours. He said, I generated this on a web, and here's his URL if you want to visit it. It's in your slides. And this is a beautiful pattern. And if you zoom in, there are patterns here. It looks chaotic, but there are patterns here. As you can see, the rightmost is 5s, then there's like 2s, and then there's a pattern, 1, 6, 1, 6, 1, 6, 0, 3, 5, 8, 0, 3, 5, 8. There are patterns eventually evolving, but it's kind of cool when you see them evolve. It's really quite cool and very beautiful when you see practical beauties of nature. So, we're talking about fixed point now still. We haven't done anything but lock in the fact that you and I are having an agreement. I'm going to send you some bits, and there's an agreement that here's the format of the fixed point, okay? Like before. So, we can do addition. Can you do things? Yeah, like addition. Easy. Look, this is, a half plus, 1.5 plus a half is 2. And it just works out. You line up the binary point, and it just works out perfectly. There's my 2. Very easy. How about multiplication? Well, here's a half times a half. What's a half times a half? 3/4, right? Okay? So, where's the 3/4 in here? The real question is, where's the energy? The energy is 3/4. It's a half plus a quarter is 3/4. Where is that? Where's my point? It's more complicated to keep track of that. Okay? And we're going to see, in general, we have a problem. And our problem is that if I maintain a fixed binary point, that locks me into some range. I really can't get to way huge numbers and way small numbers if you and I lock in where that binary point is, right? We got to do something different. So here's the big idea. Big idea number 1 so far today is, what if you separated where the energy was, which is where my 1s are, right, with where the binary point is? That's a really big idea. So separate. Rather than fix the binary point, why don't you let it float around? And when the binary point is really to the left, over here, there happens to be a binary point here, but what happens if the binary point is over here? Then it's a really small number. If we let the binary point be on the right, it's a really big number. Isn't that a cool idea? So you have, rather than lock it in and just say, here's my bits, why don't I reserve some of those bits to tell me where the point is, and the other bit is where the energy is, and now I can get my big and small numbers. You got it? That's the big idea you can learn today. You separate where the binary point is from the actual number, and now you can get to big and small numbers seamlessly. Now I can do my halves, my big numbers, my small numbers. I'm done. Lecture's over. Have a great Friday, guys. No, there's more to it, obviously. All right. So this is, by the way, we call floating binary point. The idea that I decouple a frozen fixed guy and I unfreeze it, I thaw it out. I would say thawed binary point. Fixed, dynamic binary point. Okay? So the binary point is outside the stored bits, and so now I can do big and small numbers, and that's awesome. So here's some background. You guys remember scientific notation? Here's a couple of words you might remember. You get a mantissa on the left, a decimal point here, an exponent, and a radix, which is the base. Okay? Now, the other piece of this is that we always, in scientific notation, use a normalized format, which in the decimal sense, what does that mean in the decimal sense? It means the mantissa is never any more than 1 digit, right? So it's never a 0. It's also never 0. It's a 1 or a 2, to 9. That's all it can ever be, okay? If it were a 0, then you've done it wrong. You're supposed to slide to the left and put the 1 there, okay? Or put something else there. Like, here's an example. 1 times 10 to the minus 9, okay? That's a nano something. It's not 0.1 times 10 to the minus 8 or 10 times 10 to the minus 10. It is 1 times 10 to the minus 9. There's one universal way of doing it, okay? So you normalize. This is called normalization. Normalization is the way we talk about things having some standard. You want to have a normalized standard for that thing. So, look at this. Bink, bink. I love this little slide transition. The same thing. We've done this before when we were talking about how we'd represent binary numbers. The same idea with scientific notation. Here's my binary point. My mantissa is the same. Exponent is a number. And my radix is now base 2 rather than base 10. We have our floating point. If we try to encode this number, there's our floating point. Why? Because this exponent tells me how big or small the number is. That's like where the dot is. That's my exponent. And over here is the energy. Does that make sense? It's like 101, and the dot is somewhere here in the 101. Isn't that cool? That's pretty cool. So, this is how we do it. This is how we do it. So I've got a sign and exponent significant. You might have once asked me, Dan, what was this whole deal with the peer instruction question? You said that there are 3 different encodings we use to represent the, what was my example back then, like lecture 3? It was like 0.75 or something. Some number like 1.5. How many encodings? Look, 3. There's an S field, which is 1 or 0 if it's positive or negative. There's an exponent, which we just said is how we tell you where the dot is, that floating point is, and the significand, which is where the energy is. We normalize it, and you say, Dan, ain't no free lunch. You saw that we were counting in the jumps by instructions, not by bytes. Because when you're moving in the instruction space, it's always by multiple of 4. So why store a 0 there? So you say to me the same thing, Dan, if here is my significand, why would I store this 1 if it's always a 1? Right? Normalization in the binary sense, in the decimal sense, normalization means it's either 1, 2, 3, 4, to 9. But in binary, normalized means it always starts with a 1. Therefore, that's always a 1. Now, who's smart and can guess what the problem might this be? By always locking in a 1 point something. I hear it mumbling. Run in, I say answer. Give me somebody else. Yeah, go. You can't get, what's your name? Ian. You can't get 0. Correct. So far there's a problem. Hold that in the back of your head that there's a problem with 0. But for now, forget the 0 for now. Does this make sense that we can actually do every big number or small number? I just make my exponent big, and now I've got a big number. And now the energy is here, and the decimal point's all the way to the right of it, right? Because a lot of zeros there. Or if I make this exponent really small, then now there's a dot here, and then zeros, and then here's your energy, which is your significand. Isn't that cool? And we don't store the 1 because why waste a 1 on that? So aside from the 0 part, we throw the 1 away. We store the things to the right of that, which we call the significand. And now that's my thing. This is it. This is the format. And we're done. Now, there's more details, but that's it. This is my concluding, like if you flip to the back, it'll say, and in conclusion, it's this slide. This is it. That's the big idea. There's 3 pieces to it. S, exponent, significand. But you said, Dan, there are 3 different encodings we use. That's right. S, I take from sign magnitude. Significand, we treat unsigned. You'll see that. So that's the unsigned. Exponent, we treat biased. Remember that those things? There's like unsigned, signed, which is 2's complement, biased, sign magnitude, 1's complement, significand, unsigned, exponent, biased, S, sign magnitude. Isn't that cool? And it all works out. We'll see why that is, but it's like, this is some awesome engineering, folks. I love when people explain really cool engineering, like show me how a car's engine really works. That's awesome, right? Show me how a rocket engine works. That's cool. Show me how this works. For my kind of computery, software, digitally space, the engineering that went into this encoding is really, really impressive. The more I see it, the more I'm happy, and more impressed I am with it, and the more happy I am to share this with you. Hopefully, I'm getting that across today, because I love this stuff. With this encoding, only 8 bits here, I can go down to 2 to the 10 to the minus 8. 2 times 10 to the minus 38. That's a really small number. And 2 times 10 to the 38th. I solved that slide where I said, how about big numbers, small numbers, number of seconds in a millennium, Bohr radius. I can do all that with that. It's really cool. Okay? And if I can't, I just make those bits bigger. I go to a double. And you'll see that a double is just twice the number of bits, 64 bits, and now I have more for that, which means I can go more precise, and I can also go bigger and smaller. So I win on both sides. The exponent field gets bigger and significant field, so I get more accurate, and I also get bigger and smaller as well with that when I go to doubles. We'll see that. There's a question that I saw a hand floating up. Where's my hand? I thought I saw, yeah, here. I knew I saw a hand.
Wait, if someone loads values into registers and stuff, how does the register tell the difference between the bits?
I love it. Someone loads a float into a register. T0 contains this float. How does the system know that was a float? Anybody? It doesn't. All along we've seen it doesn't. There's no way you got to remember that. You as the hand authorer or as the compiler need to remember that was a float and that you're operating on a float. We saw it from memory, same as it, or a character, same idea. Great question. More questions. This is it. That's the big idea. Pretty cool. Yes, over here. Where do floating point errors come from? What does that mean? Oh, you can get imprecise calculations. Well, let's look at this. We're gonna, as we kind of look at this, here's a meta question. Before let me see if I can answer your question by asking you guys a question. Maybe that comes up. S exponent significand. Big idea of economics, ain't no free lunch, okay? If I can go to 0 to 4 billion and all the integers in between with an unsigned, right, 4 billion-ish, how about this guy? The moment this encoding is able to encode a number that's outside of 0 to 4 billion, some integer, like a half, I have to give up something in the 0 to 4 billion. I can't keep getting something for nothing, right? I can't squeeze, right, water from a rock. I can't squeeze lemon from a rock. So I have to, if I can I do a half in this encoding? Sure. Then you had to give something up. Can I do a quarter in this encoding? Yep. Then it's something else you had to give up. Every time I tell you you can encode something with this, you couldn't do it with integer, you had to give up an integer to do that. You couldn't get it for free, right? Ain't no free lunch. So what do we give up? 0 to 4 billion. What can't we do in this encoding? Yes. Can I do 1 in this encoding? Sure. 2? Yes. Sure. 3? Sure. At some point I say stop. I stop saying sure. Go. Ah, I love it. Tell me why. Tell me why. Tell me why. Yeah, so like watch what happens. All this exponent does is take the energy, which is the 1 point significand, and slide it left and right, right? Let's say I keep sliding it left. So I slide it left so that this 1 slides into kind of the 32nd place. Does this make sense? So that 1 is representing 2 to the 31. Okay? Now these remaining x's do all the numbers from 2 to 31 minus down. They're like the bits kind of on the left side of the thing, but all the way from 2 to the 31 down to kind of 2 to the 8th or something, whatever it is. I guess, right? No, 2 to the 31, 2 to 23, 2 to the 8th-ish. I can no longer get down to those little bits. I want to like change more, but I can't because I don't have this significand. It stopped me. I don't have 32 bits of energy. Remember the energy bits? I only have 23 bits of energy. So I can slide those 23 bits of energy anywhere I want to, but it means I can't get any more to left or right of those 23 bits of energy. Remember that slide with the 5 bits? So that's the energy thing I was like? That's the idea. Yeah, question?
Can't you have a pseudo instruction to OR it so that way you can get the other numbers?
Ah. Can I have a pseudo instruction to OR? Well, it can't be from here. That data can't be. I'm just talking about, it can live somewhere else. You're right. I could have 2 floats, somehow try to be clever about it and do that. And if I had that, I might as well use a double, and a double can do everything an integer can. So if I had more bits, I could do this. But I'm just saying with these bits and only these bits, I can't get to all the stuff an integer could do.
Well, if you have only a single register that you can have this number, and you have to get the lower bits, and then can't you just pour onto it whatever you need to do, or you do some other...
I could. No, I'm saying that. You could OR onto it, but that OR comes from another place. There's just cheating. The point is like only 32 bits, I don't have those space. Right, that's what I'm saying. All right, let's keep going. So, now your question is, well, Dan, what happens? Let me keep going. Maybe come back to it, because maybe I might answer it. What if I'm too big or too small? If I'm too big, if I'm bigger than 2 times 10 to the 38th, it's called overflow, as is the negative side of it. Okay, so overflow, remember I tricked you before, I thought you said it was underflow. This is the underflow. If I want to go smaller than the smallest guy, which is minus 2 to the 10 to the minus 38, I can't get any smaller than that. So that's underflow. When I want to get a small number but I can't, or I want to get a big number I can't, that's called overflow. Okay? What would help reduce chances of overflow and underflow? More bits. That's it. Just throw more bits at the problem. And that's what people often do. So they'll throw more bits at the problem, and more bits, typically more bits in the significand or in the exponent or both. Exponent's the key thing, right? To get the size, the guy sliding up and down is my exponent. So you want more bits of exponent first. And precision might give you for the other piece of that. So here is floating point standard. This is the official standard now. This, again, the same slide before. Sign bit. When it's 1, it's negative, like before. 0, it's positive. Exponent, we're going to see it's in biased format. I'll explain what that is. And the significand, I have this. So it's 1 free bit, the invisible 1 normalized bit, plus 23 bits in the single, 52 bits in the double. So the double I was mentioning before is a lot. Remember, can I do my 32 bits of an integer in a double? Sure. I got 52 bits of a significand. I can certainly do an int in that space, my 32 in that. We know that my significand is always between 0 and 1 because it's a 1 point something. And if I throw the 1 out, it means this is 0 point something. So 0 point something is always between 0 and 1. For normalized number, we're going to see how we get the 0 case. So we're going to reserve this. Oh, look, it even says the answer. I was going to hide the answer for a while, but I actually, the slides say it. We reserve the exponent 0 for just 0. So now guess what? It was really, really fortunate in 2's complement that all zeros meant 0, because it's the same as a signed, same as an unsigned number. All zeros mean 0. Wouldn't it be great if a float, all 0 means 0? Guess what? We give that to you for a gift. So when the exponent is 0, and the significand is 0, and the sign is 0, then it's 0. But you can say, that's nice, except, isn't there also a negative 0? Oh, yeah, there is. And we have that. And there are times when that's okay. There's a slide about that, but we'll get to that. Yeah, let me, you have your hand up for a while. Go ahead.
Isn't that also 1? I mean, 1 into 2 makes about 0.
1 times 2 to the power 0 is 1.
Yeah.
So what's the...
If all significant is 0.
No, we're going to have a special, it's like a special case. It's because it's a bias, we're going to see, good point. So your question is like, if exponent is 0, it's going to turn out that we're going to play with the bias format to be able to get a 1. That's not a 0. That's still not a 0. It's 1 point this. You have to somehow remove the normalization to get your 0. When we get to the normalization part, that'll be the way that we get our 0. Otherwise, you're talking about a 1. If it's all zeros, 2 to the 0 is 1, and that's not a 1, not a 0. Because the 1 is still there. The 1 is getting the problem, yeah.
So does the S bit or the first bit signify the sign of the exponent? Or
No. Sorry, good question. The S bit, I go back. The S bit is a sign of the whole thing. The overall float. Whether it's on the right side of the number line or left side, or the whole thing is the S bit.
so if the exponent is unsigned, how do we get the sign for...
The exponent is biased. I said before the exponent is biased, and we'll talk about the bias. Bias means that you kind of start negative and count up to get positive, and you go through 0 somewhere in the middle of the binary energy. Okay, so here's the good question. Now we're at the exact question. IEEE 7. This is the floating point standard that became the standard everywhere. This changed everything. Once we had a standard, then I knew I could take my Fortran code, which is probably what it was in the day, and port it from one machine to the other. And if both machines implemented the standard, I knew I could trust the answer. Before then, I couldn't trust the answer, and you'd have missiles going right when they should go left, and that could be bad. So don't. Flying in the early days, if you had some, who calculated the auto navigation on my system? But did you port it? Yeah, we did. Did you use IEEE 74? No. I'll walk. Thank you very much, kind of thing. All right. So here's the key. We used a bias exponent for a really interesting reason. Okay. We want to be able to use integer comparisons to compare these numbers. Back in the days when we had where extra hardware was hard, we used to have floating point coprocessors. Remember the days of, who might remember the 68, 881s back in the Motorola days? We had a separate floating point coprocessor because this stuff was so hard. You often have on this expensive real estate of a chip, floating point hardware, dedicated floating point hardware to do this stuff right. So floating point stuff is important to get right, and you often are dedicating really valuable real estate to have a different amount of computation than you have in your integer units. You have a floating unit, usually. So we would love to have a bigger exponent mean bigger numbers, right? That's nice. 2's complement poses a problem that way, because if you look at the number as an unsigned, just raw set of bits, negative numbers look bigger in an unsigned way, because there's more 1s at the top. But if you use biased, then almost no, like if you remember the bias count, bias starts at, it's like, here's the graph. There's a beautiful graph. The Computer Science Illustrated project shows you these beautiful graphs of kind of like, if you just count on the odometer, what you get. And what you get is, as I count on my odometer, here's the 0 line. As I count my odometer from all zeros on my binary odometer to all 1s on my binary odometer, what am I doing in biased? All zeros is a negative number, and I just count linearly up to the biggest positive number. It's a really beautiful way of thinking about it. Unlike signed and unsigned. So unsigned does this. Go linear here, and just keeps going. Right? That's the unsigned. What does signed do? Signed does this thing, so that it exactly matches in the positive numbers, right? 0, 0, 0, 0, 1 is still 1 in both unsigned and signed. So they're exactly the same. It goes to here, and then jumps to here and does that. But this bias thing has a really cool property that when it's small, means a negative exponent here, it's all zeros. When it's big, it's a positive exponent and really big. So it's really nice to use bias for this reason. Okay, that's why I like the engineering of it. So again, here's the summary. Bias notation for the exponent. Here is the bias. Whenever you say it's a bias, if I ever say to you, hey, jump, you have to say how high. It's like I've underspecified the problem. If I say T, you have to say hot or cold. Okay? So I say bias, you say what's the bias? And the answer is 127. Okay? So that means it starts at minus 127. So thought another way, when this binary number reads, whatever the pattern for 127 is, which I know it is, it's 0, 1, 1, 1, 1, 1, 1, because 128 is that guy, this is where you get your 0. That's your 0 point, where this is 127. Okay? That's pretty cool. The bias of double is 1023. And you'll see there's a little equation that says, okay, if I have 8 bits of bias, how do I get to 127? Let's think about it. 2 to the 8th, well, it's 2 to the 7th minus 1. So n bits of bias is 2 to the n minus 1. That's how my bias, in general, with this kind of standard. Okay? So here's my number. This is the key thing that's in gray. Minus 1 to the s. Isn't that kind of clever? Watch that. S is 0. Minus 1 to the 0 is 0. It's a positive number. S is 1. Minus 1 to the 1 is minus 1. And there's my negative number in the front. Isn't that kind of clever how that little equation works? All right, people don't care. Okay. Times 1 plus significand, because remember I don't store the 1 because it's normalized, times 2 to the exponent minus 127. Okay? So when my exponent reads 127, it's 2 to the 0, and there's my 1. I still haven't handled the 0 case yet. Yes? Yeah, okay. There's my 0 guy. He's going to hit me with that. Okay. Before, I want to tell you about how impressed I am with the engineering of this and how impressed the world was. How impressed was the world with this? They decided to honor our very own Professor Velvel Kahan with the highest honor in computer science. The Nobel Prize of Computing, called the Turing Award, was awarded to Professor Velvel Kahan in 1989 for being the key author of this standard. That's how important this was fundamentally. This is a name you better remember. He's our own faculty. He's awesome. He is such a pool of wisdom. Sit 5 minutes with him and you will just learn 10 new things. It's an amazing guy. Please do make a chance to meet him if you can before you graduate. Okay, so here's an interesting question. I've got this number. Wouldn't it be awesome? Didn't I ask you one time how many bits for pi? And you said, oh, I need a lot of bits. And the answer was 1 bit for pi. It's either pi or not. Wouldn't it be cool if we can represent pi, this irrational, could we represent like a crazy number like infinity as an actual floating point encoding of infinity? And then when things get big, they become infinity. And we store infinity. And when you print out the float, it says inf, or if it's clever, it says infinity. It says that. That's really cool. So, we do that. IEEE 754 actually has an encoding for infinity. What they do is, how would they do it? If you were thinking out loud, remember we said, look at this picture. Look at this picture. How would you do infinity? Well, first of all, you might want positive or negative infinity. So the S can be 0 or 1 to say which side of the number line you are, which end of those 2 arrows, right? Exponent, what do you probably want? All ones. Guess what? That makes sense, because guess what? It keeps counting up until it gets the biggest number. And guess what? The biggest one, infinity. Significand, though, has to be 0. Okay? All zeros for that guy. So let's go through here again. So significand is all zeros for infinity. 0. You're going to say, how do we do 0? Well, we're going to make a special case in which the exponent is 0, which is small, and this guy is 0. Okay? Because this number is going to count up very much like a sign magnitude number does, in which all zeros start at 0, and as I start incrementing this whole thing like a binary odometer, in which I start this small guy, it'll get to the smallest number first. The smallest number bigger than 0. And it'll keep going away from 0, very small, 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 because this exponent is very small, and therefore this counts up from 0. And then the next thing that will happen is this will be all 1s. It'll wrap. This guy will be a 1. This will go back to all zeros, and that's now the next smallest number. And it'll actually just work. Counting like a binary odometer, it just goes from 0 till we get all 1s here. That's the infinity case. And this is all zeros. I haven't told you what happens when this becomes 1s yet. But assume that we kind of go to the next big thing, which is it wraps till you get back to here, which is this number, and then it's 1, all zeros, and now you're at negative 0, facing that way. And as I continue up, I'm now walking away from 0, just like a sign magnitude number does. Okay? So I start from binary odometer 0, I walk to this end, which is the biggest number I can ever do. Then I jump over, there's infinity, and then if I keep jumping around again, I get back to -0, and I walk this way now. Like, remember my arrows? It kind of goes this way, and then starts in the middle, goes that way, just like side magnitude arrows do. Okay, so there's some special numbers we've seen. Here are some special cases we have. So, 0, 0, 0 becomes 0. We know that 255, which is the biggest, it's FF, right? It's biggest representation of my exponent. Significand 0 is plus or minus infinity depending on the sign bit. Anything else in the middle between the 0, so exponent 1 to 254, the kind of middle guys, that's the normal floating point number we talked about. But there's two guys in red we haven't used yet. And there's this wonderful idea that he had. This is why it's so cool. It's like, who's ever had Scrapple? Scrapple is this meal I've heard about recently in which you have a pig, I think it's made out of pig, right? And you kill the pig, I hope I'm not offending the vegetarians. You kill the pig, and you normally eat some parts of the meat, and you throw some parts away. Scrapple's idea that you just use everything. You make a big stew, and you put everything. You just use it all. And that's what, in the olden days, that's what our ancestors done, right? The Indians and folks who were here many, many years before, they had the cloth for this, they used the bones for tools, they used every part of an animal. That's what we're doing here. We're using every part of these bits. We're not throwing anything away. So, let's be smart about it. We still have this region in here and a region in here. What else would you want from a floating point number? I like constants. Constants is a great idea. Let's think about that. Constants is one idea. What's, I don't know, what's square root of -1? Imaginary. That's an interesting space. You could also say, we'll consider the complex numbers too hard to do. That'll be some other, you could do that as the meta encoding, right? Somebody does 2 floats and that's, both the positive. You could, have a layer above. You don't have to encode it here. You could just have somebody else have a wrapper that says 2 floats are imaginary. But what else would you want of a single number that's not in the complex space? Couldn't you say it's illegal? Like, not a number? Aren't there mathematical operations in which the output is actually illegal? So why don't you do that? 1 over 0. Well, we can store that. That's infinity. We have a number for that. So we got that covered. So the divide by 0 is an error we'd care. But how about a square root of -1? That's really an error if you can't do complex numbers. So therefore, why not have some special numbers that say it's illegal? It's not a number. And there we are. 0 over 0 is nothing. 0, 0 is definitely an error. That's another kind. And the other cool thing about this is there may be lots of different kinds. You can see right there at the top that 0 over 0 is one kind of error, and a complex number is another kind of error. So, think about this. By having the significand be non-zero means that with every different significand, you in theory could come up with a special bit pattern for the significand, meaning that kind of error. Another bit pattern, that kind of error. Wouldn't that be kind of cool? I say arrow. Error, right? That's kind of cool. So what a great idea. Rather than a single idea of a single number, which is exactly infinity. There's only one infinity, so this is exactly one bit pattern for infinity. Well, it's 2 because it's plus and minus, but But this idea that we can have this significand be non-zero means that we now have 2 to the 23 different nans we can store. Woohoo! So party on nans. So we got that covered, okay? Now, do nans help with debugging? Sure, because they contaminate. If you have an expression, once something becomes a nan, anything that operations like a nan plus 5 is a nan. Because you had no idea what this was. It doesn't make sense anymore. Like that, you can't have 0 over 0 plus 5 and still be something that's reasonable. So nans can contaminate, and they in fact do in floating point hardware. Once one of the numbers is nan, you start operating with it, everything kind of like a black hole gets sucked into the nan. And you get a nan as an output, which is the right thing to do. So that's kind of cool. Here's a really interesting point. While they still had this free bits, right? You still have free bits. What do you want to encode with those free bits? We still have that, exponent 0, significand, non-zero. Look at this. They said, look at our number line. If we actually zoom in on our number line, we have this weird gap in here. Where you're counting by this really fine decrement, like let's count down to 0. Ready? Ding, 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 ding. I'm counting down to 0. Ding, 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 ding. Really small numbers until I get to the smallest number I have, which is that normalized number, right? Which is what? 1 point, all zeros, times 2 to the The smallest exponent is 1, because we reserved the 0. 1 minus 127 is minus 126. So it's 2 to the minus 126 is the smallest guy. Right? I just said it here. I just did it in my head. Okay? Now, what's the next one over? What's the next one over? What's the one back of that, of the smallest guy? Always go back to your odometer. Your binary, I said they're all ordered. So you say, what's the next, what's one bigger than that? Just take your binary odometer and add 1 to it, and that's the next biggest number. It's always going to be that true, except when you wrap the sign magnitude line. Okay? So the next biggest number is, there's a 1 over here in the significand. So it's 1.01 times 2 to the minus 126, which we just agreed was the smallest exponent. Okay? So what's that? Well, that is, you over here, this is 2 to the minus 120, 2 to the minus 23. It's 2 to the minus 126 plus 2 to the minus 149. And you're going to realize that I've been counting by 2 to the minus 149 every time. 2 to the minus 149. I've been subtracting linearly by 2 to the minus 149 in these gaps until I get to the smallest guy, and then I have this huge gap, which is 2 to the minus 126 away from there. All these numbers are so big, you're kind of getting confused in there. But there's a big gap. The spacing between A and B is smaller than between A and 0. That's what I'm trying to get to. Okay? If you get lost in the math, don't worry about that. So what can we use those bits for? Just line them up. Just stack all the bits in there to kind of fill that gap, which is exactly what we do. We fit them in there, and it works perfectly. It fits in just perfectly so that those are now small. But how do we make them small? What was the problem? Why couldn't we do 0? Go ahead. The 1! That darn normalization was killing me. So what if we took the 1 away? So we take the 1 away, and we have no leading 1. We call these denormalized. Remember, the normalized was the problem. The normalized meant the 1. We take the 1 away, now the number is denormalized. It's not normalized, so it's denormalized. We call these denorms. No leading 1, a leading 0. However, to make it work, you can't use the equation anymore, which is take the exponent, which is going to be a 0 now, and use it in the normal way, because you'd have 2 to the minus 127. You have, to make it work just right, you have to make an implicit exponent of 2 to the minus 126. And then it works out right. Okay? So, it fills in perfectly. And it literally fills in just perfectly. It counts by this thing, and then it goes to the next line. It starts counting by more, and it's perfect. It's really happy. See, look. The smallest 2 are exactly right. I love it. So, we're very happy with our denorms. Yes, question? I guess that's true. I guess if you consider us having a total of 24 bits that control it, like 1 point, blah, 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 and now I know there's a 0, I guess I give up the leftmost bit because there's no 1 point anymore, but there's still energy there. It just happens to be the leftmost guy is 0. It's still 24 bits of it. It's just the leftmost guy isn't fixed anymore. So I now feel like I have full power over 24 bits, really, right? When it's a denorm, it's 0 point something and I store it here. If it's not, the 1 is there and I got the covered. So in a way, I kind of get it. I get 24 bits for free out of the 23 is what it is. I use it 2 cases. Okay, so there's my denorms. And now I'm done. We have now done a great job. We have room for all 2 to the 23 different nans. We love that. We got our infinity. We got our floating point thing. We got our denorms. And the beautiful property that as I increment the binary odometer, I start from 0 and I walk to the smallest denorm. Right? Because it's 0, 0, 0, 1, which is the smallest denorm, which you just saw was 2 to the minus 149, I believe. And then you keep counting by the same linear unit. Until, I'm going to do an animation for you. And this is a key animation people always forget. Remember, the exponent tells you where the dot is. Right? That's where the floating point is. Said another way, the exponent tells you when you increment the right part of the odometer, the significand, it's how big your steps are. And they're all at the same exponent. So as I'm counting by 1, as I'm incrementing by 1 in the rightmost bits of those field, I'm always taking equal size steps. Until what happens? Until the significand becomes all 1, that wraps to 0, exponent increases. Now what do my steps look like? How does it compare to what I was doing? Twice as big, because I increase my x. It's 2 to the x. When you increase x by 1, it's twice as big. So now I take double steps, okay? Until what happens? Significand fills up, wraps over, exponent grows by 1. Now I take twice as steps again. And that's how I get to really small to really big. Because I take these linear steps while I'm still having a fixed exponent until exponent changes and I double my stride. Until it changes again, and now I double it again until I'm taking steps by not 1s, not 2s, not 4s, but I might be stepping by 1024. With every 1, I'm stepping by 1024, right? And then 2048, and then 4096. Isn't that cool? What's the missing piece of that? What about all the integers I skipped? That's why I was taking giant steps, like the game. You can come with giant steps. Remember that game where you would like come with monkey steps and then giant? Okay, I'll take giant. When I'm taking giant steps, what have I lost the ability to do? Put any numbers in here. I can't get to the middle because my only float, like these two floats differ by 1 bit. But I can't get in the middle because that's what I had to give up. That's what I had to give up to be able to get to that big range, right? Ain't no free lunch. To get the range of small to big, the moment I had a single number that's outside of 0 to 4 billion, I had to give something up. And what I was giving up is that fine granularity at big numbers, but who cares? Right? How far is the Earth away? How far is the Earth away? Right here. That's exactly 6 feet. How far is the moon away? How far is the moon away? The moon is... Is it that plus a foot? Who cares? It's that big. It's that far away. I'm counting by, millions of miles here. Who cares? All right. Love it. So, conclusion. And now, here's the best part. This is the coolest thing. Watch this. The web is great, not just for watching people do float videos, but watch this bad boy. This is incredible. Watch this. Bam, bam, bam. This is an applet, which you have to have, folks. This is so good. Oh, Billy. Okay, look at this. All zeros. These bits are all zeros. Therefore, my number is 0. Look, my number I'm actually representing is 0. Let's now count up by 1. Ready? Remember, I'm 0, right? I said it was 0, 0, right? Now watch. This is, all zeros and 1 is the smallest, what? D norm, right? Come on, all together. Ready? Here you go. So watch. I make this a 1. That's my smallest number I got. Okay? Look, it says denormalized, and my sign is +1, so I'm positive. Exponent is minus 127. I think it should be minus 126. It's minus 126, actually, and that's the thing. It's because it's a D norm. Anyway, but the number is right. Here's the hex representation. Here's the binary representation. Here's the actual number. Okay. You say, but Dan, how do you represent 1? Let's figure out how to represent 1. How do you do 1? Let's work it out. Come on. 1. What's the S bit for 1? 0. Come on, 1. E. Okay, so S, E, M. Okay, what's this guy for 1? 0, right? Okay, let's try this in exponentially. 1 times 2 to the 0. How do they make this 2 to the 0? Make it, there's a bias here. Make it 127. What's 127? 0, 1, 1, 1, 1, 1, 1, 1. Oh. Is that awesome? Here's what's cool about this applet. Here's what's cool about this applet. I could have just typed a 1 and it would give me the answer. So how about a 2? How about a 2? How about a 2? That's 2. Why? Why? Because my energy, remember, you're forgetting that there's energy and there's where it is. If I'm representing 2 in binary, there's just 1, 1. And the only question is, where's my dot? But this 1 I get for free. Meaning this is 1.000. So this is my S. That's 0. That's why the right part is 0. Okay? But to make it 2, the dot has to be here. So my exponent better be 1 times 2 to the 1. Therefore, to make the overall thing 1, it's this number minus 127, which is 128, minus 127 equals 1. Therefore, that's 128. It's kind of useful to know that 1 and all zeros in an 8-bit guy is 128. It's kind of a useful thing to have. Okay? How about a half? Ooh, how about a half? A half. How about, maybe you can't do the expression. How about 0.5? Bam. 126. Because that guy has to be minus 1. Oh, I make it harder. How about this? How about 3/4? Oh. What do I do here? I must put a 1 over here, right? No. What's 3/4? Let's go back. 3/4. Come on. Where's my big? I had a nice thick piece of chalk. Where's my pretty? I had this really. Here it is. Okay. I love this big one. Okay. 3/4. First, write it in binary. 3/4 is what plus what? A half plus a quarter. 0.11. Getting to this is half the problem. If you get this, it's like half the problem. If you can write 3/4 in just fixed point, that's it. What's this really? In normalized form, 1.1 times 2 to the, how much does this have to move? Minus 1. Guess what? I already have 2 to the minus 1 represented by this guy, which is I'm doing a half. This is a half right here. So that doesn't have to change. The exponent doesn't change. I already got this guy. The minus 1 has already got blocked in with my 126 in my bias. If I just talk louder, I kind of make the information sink in deeper. That's my theory. If I just keep getting louder, it just kind of gets more success. All right. So how do I get 3/4? Is the 1 over here on the right side? No. It's on the left side. It's 1 point this. It's 1 point this. Therefore, it's 1.1 3/4. This is an incredibly useful tool as you are playing with this to test yourself. Can you do 15 and a 16th? 15 and a 16th. How do you do that? I don't know. Well, you can type 15 and a 16th, 15.0625, because you memorize that, and there it is. Or you can work it out. That it's got to be 1111 for the 15th, and then 0001, which is, watch, 1 for my normalized, 1110001 for my 16th. Times 2 to the what? 3. 2 to the 3 is 128 plus 2. 130 minus 127. That's 128 plus my 2. It just makes sense. This is so cool. How about this? It's like, but Dan, this can't work for everything. I mean, come on, you got 40 seconds left. You couldn't possibly give me on all ones here. I mean, this is going to be, what would this be as I fill this up? Tell me what it's going to be. Oh, it's so good. It just feels good. Folks, you are now part of the elite 5% who know this stuff. Okay, how about this? How about a 1 over here? Nan. I feel like some Indian food. Anybody? Okay. Nan is like a bread. No, that's not joke. Oh, no joke. All right. On that joke, I'll end it. Guys, have a great weekend. That's floating point. All right.